Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Okay, I'm back here in the Driven studio. It's been about 3 months. I took a little time off while I was working and did have some holiday time. But then over the holidays, I started thinking about a project. And this episode really is the culmination of that. It was a project to try to project AV timelines. Okay, sounds like I had a lot of fun over the holidays, and maybe I should be doing other things besides cranking through mathematical equations and what have you to try to figure out when AVs will come to be. But I often get asked the question, as I'm sure many people who are in this space get asked, as I've seen, hey, when can I get in my car and just have it take me to wherever I want to go, where I can just kick back, go to sleep, and then tell it to wake me up when I get there. Questions along those lines, or maybe they want to do some work, maybe they want to play a game of Parcheesi or something. But nevertheless, that question comes up a lot. And of course, I've been in the space for 20 years, and I've seen all kinds of projections ranging from the way optimistic, like, hey, we're going to have it next month. It's going to be next year. Full autonomy um, is just around the corner. And then year over year, you see sort of those projections slipping. And then you hear the most pessimistic of projections where they say, it's never going to happen. We're never going to have autonomy. There's too many edge cases. It's too long of a tail, as they like to say. And then there's the Goldilocks principle, where you try to kind of say, well, what's just right? What's the right what's the right estimate here? And all of this is, including my own, has been by and large qualitative gut feels based on experience in industry and where you see things going. So it is, these are educated assessments, but nevertheless, it's all just sort of um, intuition and guessing, by and large. There are, some people probably have taken a few quantitative estimation whacks at it, but I thought I would try my hand at that over the holidays. And again, with um, I guess almost 20 years in the field, I have talked to a lot of different folks. I've read a lot of different things. I've watched and companies and people and presentations, and I thought, well, you know, maybe I can take some of the things that I think about that contribute to um, this time frame for when AVs will come to be, and provide a system level kind of quantitative model for it, right? And why not leverage sort of the latest AI tools that are out there as well, which can provide pointers to different methods for mathematical modeling. Of course, you've always got to, check what the recommendations from these AI tools say, but but leverage some AI tooling at the very least for formatting the paper. And oh, by the way, yeah, create a paper, right? And you'll see I refer to um, we in the paper because I have leveraged some of these tools, but I cranked through some of the math and tried to figure out, is there a way to quantify, um, at least bound, get some relative sense between the different types of autonomy, when autonomy may come to realize this SAE level 5 full autonomy, drive everywhere under every condition situation, broad commercialization. When will we have? When will we arrive at that point? And so I created a paper, and true to the standard rule for creating most papers, I gave it a really long title. It's called A Comprehensive Mathematical and System Level Analysis of Autonomous Vehicle Timelines. The subtitle being Integrating Complexity Theory, Reliability Growth, and ODD Modeling. So I felt it was important to give it a long title, just so that would fit in with all the other long title papers out there. and hence the name. But it does accurately describe what is in the paper. And so what I'm going to do here in this episode is just give an overview. In a future episode, probably in the not too distant future, I'll do a more detailed step by step walkthrough of paper, in terms of the math involved. Throw up some of the equations on the screen, and we'll talk about those and some of the assumptions made, what have you. But this, you can consider this an executive summary or just an overview of really what is in the paper itself. So, section 2 of the paper begins with complexity-driven analysis, and what that means is trying to create a quantitative mathematical model for how long it's going to take for us to get to um, AV technology readiness, right? So let's look at the complexity of the problem and try to project when the technology will be ready to meet the demand. And again, I'm thinking here by and large, level 5, broad commercialization, autonomy. I'll be talking about stages of autonomy, but that's kind of what is really what's driving this. And so, with autonomy, one of the first things we do is look at sort of the complexity of the environment, all the objects that are in and around the space, and try to bound the compute and the technology required based on that. So we look at the state space, if you will, for the number of objects based on the number of objects that are in the environment. These objects are vehicles, people, cyclists, dogs, cats, animals, other things that you might want to avoid, or maybe, not necessarily avoid, but in the case of vehicles, interact with because you may be pacing behind another vehicle. There's other features in the environment, traffic lights and what have you, that you're looking at too. So what are all these objects that are in the environment, and how do we bound the complexity based on that? These objects can have a number of different attributes associated with them, maybe uh, discretizing the different values that those attributes can take on. And based on that, get sort of the compute demanded from the autonomous vehicle application based on that, right? So that would be considered a very naive approach to computing and bounding the complexity, but it is bounding the complexity nonetheless. The HPC, or high performance computing requirements, can be very high just based on sort of those naive calculations for how to address that level of complexity. So in reality, and we reflect this in the paper, the algorithms, and there are certain considerations that can be made to reduce the um, the state space size, right? So, and some methodologies for sort of estimating based on objects that are super far away. You may have to process less because, as objects that are very up close and near to the vehicle, because they're not imminently in danger of being collided with. So, some of these and more are some of the considerations that actually reduce the complexity of the state space, give a more practical compute bound, and based on that, we sort of refine what's the projected compute time frame and technology readiness time frame based on that, and based on Moore's law growth rates, we can also compute the time it's ultimately going to take to achieve that. Um, Now there are also some special considerations for the fact that we are working by and large with embedded computers that are in vehicles versus computers in data centers. So they necessarily start out with the current, available compute is obviously less than what you would get in a data center, of course. And then there's the automotive sort of mission critical aspect of what autonomous vehicles address, in that the pace is a little slower for technology growth because there's more um, uh, verification, validation involved with these systems, and it can slow down the path to growth a little bit with respect to the technology. You can't just put in to a vehicle, what's available today, for a consumer isn't not necessarily what's right for a mission critical automotive application. So basically, we end up with the year to reach these compute targets and roughly correlate it to the technology readiness. We assume that just because the uh, compute readiness is there, 10 years from now or 5 years from now or whenever it may be, depending on the application, that the it's you're not going to start at that point to develop the algorithms to leverage that compute available. In fact, it's these processes are happening in tandem, where you have um, uh, folks working on algorithms and of course advancing their AI technologies and other technology to leverage the compute and even drive in some cases the compute that's needed. So it's a very synergistic relationship. So, but nevertheless, we do bound it on the compute required to satisfy the state space complexity driven by these autonomy applications. So that's one facet of modeling, and that's covered in uh, section 2 of the paper. Then in section 3, we look at timeframes from another perspective, sort of the reliability growth modeling perspective. We can look to the literature and model development and test time needed to prove, and in this case, with respect to autonomous vehicles, prove that we met or did better than the acceptable failure rates of human beings in driving these vehicles. Like, what are the acceptable number of fatalities per mile, if you want to measure it like that? One could say, well, there is no acceptable number of fatalities, but in fact, we live with that now, with the 40,000 some deaths there are in the U.S. alone per year in cars, vehicle accidents. So maybe we want to do, 2 times better than that with autonomy. Maybe it's more. We parameterize that, but that's the facet of growth, reliability growth modeling that we incorporate in the paper. And one model that we lean on stems from this Crow AMSAA or power law type modeling, where the we compute a mileage requirement, which is a function of failure rates, this failure rate, certain constants, and an estimated severity level for this particular autonomy application. So it's not, a failure incident may lead to, in one vehicle platform, fewer fatalities than, say, another vehicle platform, right? Like highway trucking, one can logically assume that if there's a catastrophic failure with a tractor trailer on a road, it's going to lead to more deaths, that one failure incident, than, say, a smaller, consumer auto vehicle on a road. Of course, it will vary, but generally across applications, we can consider different severity levels. So that is also factored into this, and the to get sort of how many miles of operation do we have to prove out sort of the failure rate. And there's also another way to look at it with what's called Poisson based reliability calculations, and that is also included in the paper, where you compute this mileage requirement as a function of a failure rate, but also sort of the desired confidence level that you want to have. Do I want to be 100% confident? Obviously, that's you can never be that. Maybe it's 95%, 99%, and also we include a safety factor to get to that. We want to be 2x or 3x better than human beings, and so there's another sort of perspective for how we compute the mileage demanded to prove that we've met the desired target acceptable failure rate for this application, right? In terms of the testing that needs to be done. Um, then we have now we want to compute how many years will it take to of this testing to get to that based on the demanded miles that one has to put into the system based on those two models, Crow or Poisson. And so we take the annual testing capacity of a program. How many miles can we actually test these vehicles per year? How many miles can we accumulate of test miles, be that real operations or real world testing, I should say, or simulation, a combination of both. What's our annual testing capacity? So if we divide the sort of the mileage requirements from either Poisson or Crow calculations divided by the years, we can get, or divided by the annual testing capacity, we can get the years. And then you just can't look at that alone. You also have to consider operational design domain, or ODD, complexity factors. Some environments are more complex than others. An urban environment is more complex than, obviously a parking lot, but that's certainly more complicated even than maybe a fixed route around a downtown location or a campus or what have you. And then there's also an ODD reduction factor that we consider as well, where you can say, well, during this stage of our deployment, we're limiting our operational design domains by about a half of what the ultimate would be for broad commercialization. So maybe stage two is half of stage three, which is broad commercialization in terms of the ODD operational capacity. So ODD complexity and ODD reduction are two factors as well. So then in section 4, we look to kind of combine all this, and also we throw in the time it takes for production and regulatory procedures to take place for a particular vehicle. In other words, on day one, when a technology is ready, you've got the hardware and the software. In a typical, certainly consumer automotive situation, it takes 3 to 5 years before what you have makes it out the door to the consumer, right? Because there's just a production time frame involved with that. And likewise, there's some regulatory timelines that are evolving for our space, but we make some basic assumptions. It may be 3 to 5 years total for an application. It may be a little longer for some. It may be shorter for others. Right, the total production and regulatory timeframes. And then we look at sort of the Crow-based reliability modeling and the Poisson-based model, and kind of say, well, the Crow-based modeling is really best applied to testing the developed system over and putting it through a number of different scenarios, and how do we get to this required mileage number, and how many years is it going to take to test. And so that's a little bit different from sort of the Poisson based modeling, which we can kind of consider more of a QA test, or once everything's frozen type thing, so that we know that we've met the target rate based on a desired confidence level to achieve that, and a safety factor. So we serialize that a little bit. We add the Crow based number to the Poisson based number, and then also look to parallelize as well, because the kind of the development test work, that's, if you want to look at it like that, for the uh, time period involved with getting the test mileage from the Crow model, you're not going to be just doing that once you meet the high performance computing milestone. You may be doing that in parallel and it growing with the compute that becomes available as well over time. So we take a factor where we factor out a portion, say 70% of the time frame for Crow, and we take the max between that and say the time frame from the compute bound, and then add in the remainder, and then the Poisson based time frame, the production and regulatory time frame, and we come up with this unified AV timeline model. So it's a bit of a foot race between when we can reach the technology readiness for these applications and the Crow test portion of this modeling. And then we add in, as I mentioned, the remaining time from crow-based reliability growth, Poisson-based testing, and the production and regulatory timeframe that may be involved with a particular vehicle. And we look at this according to stages, right? Stage one, maybe pilot and limited deployments, which are happening now across pretty much every category of autonomy. There's even some early, I would say partial, but early revenue service deployments in the robo-taxi space and industrial mining applications, and maybe even across the board, some early and partial revenue service deployments. But really, when we consider when have we gotten to stage two, we would consider when is it at that sort of level of full autonomy for revenue service deployment where you don't have remote intervention, teleoperation just taking place all the time, as is the case we hear in certain robo-taxi deployments. Um, when is that requirement relaxed such that we have true full revenue service operations? And then stage three, broad commercial adoption, level five autonomy everywhere, anywhere, under any sort of condition for these applications. And we do look at the different categories of autonomy in the paper, and we've chosen eight. I've chosen eight. There's of course consumer automotive, the Teslas and the Ford Motor Companies pursue and with respect to L5 autonomy, robo taxis, what's going on with Waymo, and prior to the end of this past year, I should say, geofenced vans and buses. These are applications are happening in sort of fixed environments, uh, downtown transit type applications and campuses, highway trucking. There's a couple different companies involved with automation of tractor trailers on the road for logistics. There's delivery van type applications, kind of very similar to geofenced, passenger vans by and large, but just in this case, there's no passengers, you're delivering goods. Then also bespoke shuttles, which are also called by some purpose built shuttle platforms. These are these more newly built, I should say, vehicular platforms that above and beyond, sort of apart from the autonomy, but leveraging autonomy. They're just new, electric or other forms of platform that are being built and deployed into these autonomous applications. And then military defense applications and industrial slash, say, mining applications is another category that we look at. So we look at eight categories of autonomy. And in the paper, we talk a little bit about the current sort of deployment status as of end of 2024. And what's going on in sort of the consumer space. By and large, there's a lot of L2, L3, really limited L4. Robo taxis are the stuff that's going on with Waymo and prior to the end of this year, Cruise. There's mining applications that are more fully deployed than at higher levels of autonomy than some of these other applications that I mentioned. Certainly, highway trucking is there's been some platooning and corridor tests, and those tests are advancing, but it's still very much in the pilot stage. So based on this, and section 7 of the paper is where we take all the modeling that we've talked about and sort of the current categories and their current status in these sort of stage one pilot and some limited stage two revenue generating service applications, and we sort of outline what our assumptions are with respect to the parameters that feed the model, and start making calculations and seeing what the model yields. Um, Obviously, I iterated over this a little bit, and so the model evolved as I learned about things that might be missing. But where we start out first is we look at across these different categories of autonomy. Um, what's that number n, the number of objects sort of in the environment that sort of drive the complexity. What's the ODD complexity, and the parameters that feed that and how they vary across these different applications. And then um, we end up with sort of a compute sort of demand, and one of the sort of I don't know if you call it a revelation, but one of the derivations from the calculations are that the compute is pretty much there for all of the autonomy applications except or categories except for say consumer auto and robo-taxi right now, since they have a higher demand in terms of ODD complexity and objects that they encounter. So it's kind of speaks to the what we're seeing too in the real world with respect to edge cases and the long tail involved with getting to broad commercialization of those applications, the longer tail. And then on the reliability growth side, we take human driver acceptable fatality rates. We see that the severity varies across these applications. I mentioned highway trucking higher than, say, consumer auto, um, robo taxis, uh, higher than consumer auto, maybe in some cases. The geofenced applications and what have you, like operating at slower speeds, too, may have lower severity values. And that also speaks to the ODD complexity and the reduction factors as well across these. The ODDs for geofenced and delivery vans and even highway trucking can be arguably much less complex than what a robotaxi or a consumer automotive L5 application is going to have to address. So we outline those factors, come up with an aggressive, kind of figured out in the process of drafting this paper that the test capacity has to be pretty significant, about 1 billion miles per year. Um, because if you start taking any, if you use numbers any less, then as what's driven by the Crow-based reliability growth model, your timeline projections just go out the window. So, so there's a factored in large number of test miles per year that's required for these programs, and chose a number that we think is realistic based on uh, test capacity with simulation and real world testing. Um, and then there were a few surprises, and I'll speak to the end result at the end here, but the Crow-based reliability growth models really drive some uh, large numbers based on what's required to uh, to meet that the demands from that model. But then we see from the Poisson-based timeframes, which are more akin to the sort of the QA. Once you have a frozen system type application, might be a year, and then that can be reduced if, for some of the applications which have smaller um, uh, ODD complexity requirements, right? So we take all that and we calculate total AV timeframes based on all that. So a couple surprises come out of the calculation of the total AV timelines, and a couple things that are pretty much in line with what we would have expected. There's industrial mining. It's among the earliest of timelines that we would expect to come to be, with total AV timeline projection of about 5 years for broad L5 commercialization stage three. While partial revenue service is already occurring, their full sort of stage two revenue service level is projected about 2 years away. So we get to about a year 2026 to 2029 for stage two to stage three type timeframes for industrial mining. And on the heels of that, very close, is military and defense. Very similar in some regards in terms of their ODDs, arguably. Again, there's some assumptions made, and those are outlined in the paper. But the total AV timeline for these applications is about 6 years for stage three. So we're looking at about 227 for stage two, 2030 for stage three. Right now, these numbers that pop out of these models are rough timeframes, and we can look at this as sort of a relative factor. And I'll talk a little bit more about that across these different categories. But nevertheless, delivery vans and geofenced vans and buses end up with very similar timeframes. For delivery vans, with their simplified ODDs, they have a near horizon commercialization target of about 8 years, right, for broad L5. So 2020 or 2032 would be the time frame. We're using 2024 as sort of the baseline year, and stage two, 2028, right? So similar thing for geofence vans and buses. These again are operating in uh, scaled back ODDs, and they kind of share the reliability and scale growth path of delivery vans as a result. So stage three commercialization is the same, 8 years, 2020, 2032, and 2028 for stage two revenue service at sort of the scale that one would expect, where you have no to low human intervention at that stage, right? Versus a lot of remote teleop and remote intervention. Um, so revenue service operations is actually happening now in this particular space. I happen to know, as well as some of the others. But again, the stage two, where you have low to no interventions whatsoever, and it's at a stable sort of level, is projected at 2028 from this model. So now we turn a little attention to bespoke shuttles, aka purpose-built shuttles. They have a longer path to both safe revenue service, you could say, and certainly broad commercialization compared to the geofenced counterparts and delivery vans. And this is driven by demands of the reliability growth model, slightly higher severity levels, and additional sort of production and regulatory timeframes, right? So this model yields 35 years for stage three and 20 years for stage two revenue service sort of stable. So we're looking at 2060, right? So now these numbers are getting a little bit larger, um, and it starts to start as I got through this. I said, "Are these? Is this absurd? Is this right? Is this um, jive with what I think?" And again, this is a quantitative driven approach to AV timeline projection. I've done, and we've all done, the qualitative thing, the gut feel, and based on the model, which you can read, and again, I'll go through in detail in my next or an upcoming episode. But the paper outlines sort of the model based on this complexity and reliability growth, and you can see based on some of these factors, which are based on these aren't like new invented ways for doing reliability growth modeling, but just applying it to the AV space, we see that we start to get these larger numbers, and it gets even larger for consumer automotive because of the high ODD diversity that a consumer automotive application will have to handle when you buy a vehicle. If it's going to be an L5, a fully autonomous vehicle across all conditions and environments, that's going to be a lot of environments. It's going to be pretty much everything that you would encounter if you're driving a vehicle that you've bought from a dealer. So there's some rather large compute technology readiness hurdles as a result to combat that, and combining sort of the production and regulatory cycles plus the needed time for just further testing, we end up with 30 years to stage two and about 43 years to stage three. So that's huge. That's large, right? That's 2067 for broad commercialization of L5 for consumer auto, 2054 for full scale revenue service commercialization, right? So again, I'm more focused on stage three here. So the stage two numbers are, just focus less attention on those. But just to say that um, s- obviously stage two has to happen before stage three, uh, and uh, and the time frame for consumer auto is out there. And for robo taxis, surprisingly, due to a couple of interesting factors, which I'm going to be looking at ways to getting more, empirical information, as I'll mention. But with sort of the most demanding, uh, one of the more demanding complexity environments, dense urban ODDs, and I've kind of marked it as higher severity on sort of the blended average sense because you've got a robo-taxi application where you've pretty much got, one or more passengers, and then if there's going to be a collision, there's be other vehicles or pedestrians involved. Whereas with the consumer auto application, that sort of blended average sort of evens out a little bit more. So we chose severity level 1 as the baseline for consumer auto and 2 for robo taxis, right? So it does affect the timelines a little bit with respect to that Crow AM SAA reliability growth horizon. So as a result, stage 3 broad commercialization for robotaxis is 2081 and stage 2 is 2051. Now one can argue, well, hey, Waymo, they're doing revenue generating service right now. Well, they are, and it's partial. They're doing it in a couple cities at the moment. It's not broad across the continental U.S. or the world at this point, of course. But also, there's a lot of restrictions, limitations. Currently, they're still getting in unusual situations that to this day. For obviously some people these are smooth rides, but we saw last year vehicles drive, just at the end of this recent year, vehicles driving on the wrong side of the road. And there's apparently a lot of remote intervention and remote operation of some of these robo-taxi applications, right? So at least the reports indicate that. So stage 2 may actually come a little bit sooner, but we've got stage 3, level 5, um, broad commercialization as 2081. Then, sort of the most surprising for me, as with respect to the model, made me think about, um, is this model, did I do the math right? Is the model fundamentally flawed? Of course, we'll continue to look and refine the model, but basically with highway trucking, because we consider a higher severity level, if we choose the baseline for consumer auto as 1, I think we chose highway trucking as 5, because you can imagine one incident which leads to a fatality will very likely lead to more fatalities. If you have a tractor trailer operating on a public road with other, vehicles on the road, you have a high speed, high mass vehicle that can collide with other passenger cars, with families of people. It can, of course, collide with more than one vehicle, given sort of the size of these tractor trailers, and again the inertia that they have behind them in these situations is extraordinary. So we do put the severity at a higher level, could even be at a higher level than that, but we chose what we thought was sort of a reasonable level. And that, and combined with some of the other factors, again, the speeds of these vehicles, the ODD complexity on the one hand can be simpler because it's highway driving, which is arguably simpler than driving in a dense urban environment. Um, the time frame is off the charts, right? It's not even like, I compute a number, stage 3, 2253, obviously plus or minus 50, 100 years, I don't know. But um but it's an extraordinary time frame, right? So, and of course, by that, if there was a situation where it was really going to take that long, then the need for even tractor trailers as a transit mechanism is in question, because it's so far in the distant future that we can't even begin to predict what um what life would be like, and how logistics and will change in that time frame. So it's really it's more like not a number. It's just a large number, and that may sort of speak to the fact that this is an application that will just never come to be, right? And some people say that. Um, I don't want to put um, the kibosh on innovation or anything, and sort of the pursuit of greater things, but again, just driven from a quantifiable mathematical model. Um, this is an intractable, solution for autonomy, and qualitatively and sort of gut. I always personally thought about, well, gosh, how will I feel when I'm driving on the road next to one of these tractor trailers, and if something goes wrong, it's just game over. Now, this may also speak to mitigation techniques where this application changes such that, there are dedicated, lanes, right, for the tractor trailers, and it's isolated from public road traffic and what have you. So, but that's not the current application that most, folks who are in this space are sort of targeting, at least at the moment. So, those are the timelines by category and stage. We've got, again, industrial mining and defense and sort of the next level, stage three, in 4 to 5 years. We've got delivery vans and geofenced vans, passenger vans on the heels of that. And then, you might consider those the top four most realistic categories for autonomy based on this quantitative modeling, for what's, commercially viable in the immediate sense, but that bespoke shuttles have a longer time frame with respect to just the vehicular platforms, and in conjunction with, you've got more than a couple complex problems happening at once. You've got autonomy, which is a complex problem. In fact, it's the world's most complicated problem, autonomy, coupled with building a brand new vehicular platform, right, which has to be tested for crash worthiness and all the safety parameters that existing FMVSS and roadworthy, and crashworthy vehicles have already been tested against and proven over time and with their test programs. And then you have, in many of these cases, also vehicles that are, electric. So they're relatively new powertrain applications. So that's further out there. And then consumer auto and robo-taxi, very closely related applications in terms of their ODD complexity in some regards, at least their peak ODD complexity. Much further out there are the projections than sort of what we're hearing from the folks who are saying that this is just around the bend, right? L5 broad commercialization. And then highway trucking off the charts. Never going to happen. That's the math conclusion. So, just a couple interesting facets with the results. The categories with limited ODDs, or fewer interactions obviously appear the soonest. That's the ones that I mentioned: industrial mining, military defense, followed by the geofence shuttles and the delivery vans. The consumer focused categories like robo-taxis and consumer auto certainly require much longer horizons, again, driven by complex environments and sort of the known edge cases and long tail that comes with that, right? And so that's factored in. And then the higher severity applications lead to even longer time frames. I mean, we just talked about highway trucking and how that's an exceptionally large time frame. Is it an absurdity of the model, or is it, just the reality of what that application faces? And then broad L5 commercialization is really going to take decades for some of these other companies, certainly like Bespoke shuttles, robo taxis, consumer auto, versus kind of what we're hearing from the more qualitative or maybe emotional based projections. Although, these numbers look large, much of the reliability and high performance computing ramp up occurs in parallel. Early pilots and some restricted ODD deployments are still evolving. The final step, though, stage three rollouts require near zero interventions, high confidence, and stable hardware software platforms, right? So kind of the conclusions here are, um, industrial mining, mill defense immediate, geofence van buses and delivery vans imminent, bespoke purpose-built shuttles further out there, consumer auto and robo-taxis decades much further out, highway trucking, is it even viable? So I hope you enjoyed the podcast. Hope you enjoy the paper if you want to read it. And again, I'll provide an updated another podcast episode which kind of walks through the paper for the mathematically inclined to in a little bit more detail. But we've again quantified AV timelines with this sort of paper that using this unified mathematical model, not just relying on one sort of simplified model, but other models and the fusion thereof to sort of see what kind of projections we can get from looking at this problem from these different perspectives. Again, those being computational complexity, reliability growth modeling, ODD considerations, and others such as production and regulatory timeframes and what have you. So there's certainly some future work that I've been, considering along the way. Probably the biggest would be empirical fitting of these constants that were selected and used based on just heuristics and sort of relative analyses between the categories. That's certainly an area of future work and potential research, above and beyond just evolving the model. Also ODD complexity estimation, a better approach for that, kind of related to that, but how do we better estimate the ODD complexity? We have factors included, but again, is there an empirical or a mathematical way to sort of derive those values? And then what kind of timelines can be produced from more parallelization of testing? Is there any sort of synergy from infrastructure and regulatory related changes that could bring CV to X type infrastructure, vehicle to vehicle, vehicle and infrastructure type communications that would accelerate the path to autonomy for a lot of these applications? Is that needed? With these large timeframes, does that become a national imperative to bring safe and reliable autonomy to the masses sooner? And then also, what can sort of improved simulation bring us? Can we sort of reduce the time frame, reduce that CRO ASMAA based testing time frame down to a more realistic year estimate by being able to increase our annual test capacity, test miles, based on super realistic simulation, maybe driven by generative AI too, right? So these are some things that I'll probably be considering, time permits, with future work. And that's it. I hope you enjoyed this episode. I'm sorry it's been a long time since the last one, but I've got some good ones coming up, including some interviews, and again, I'll be diving into details of this paper and another one coming up in a future episode. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.